Equilibrium. What is it that's so equal about equilibrium? Up until now, you may have been led to believe that all chemical reactions go to completion until one reactant or the other runs out. And certainly this is true for your favorite combustion reaction. This is not true for many, many other reactions. The state at which the reaction appears to stop before one reactant runs out is called equilibrium. It looks like the reaction will have stopped because the concentration of the reactants and products remain constant. However, don't be fooled. Although it may appear as if everything has stopped, there's actually quite a bit of activity, and sometimes we call this dynamic equilibrium. What's going on is the rate of the forward reaction will equal the rate of the reverse reaction. So we might start with some reactant, represented by R, with a big letter representing lots of reactants, and a fast forward reaction. As some R proceeds, the quantity of R will get smaller, as represented by each letter. And notice that the arrow representing the forward reaction is getting smaller each time. As we build up a little bit of product, the reverse reaction will start, and we build up more product. Faster reverse reaction it will continue, and at some point, the rate of the forward and the reverse reactions will be the same. That means that every time a reactant turns into product, some product will turn back into reactant, and the quantities will stay constant. We represent those quantities with an equilibrium expression, right side over left side. We could also reach the equilibrium position by going backwards and starting with some product, represented by P. Notice I'm starting with a smaller quantity than before. So the reverse reaction is happening. As P gets used up, that reverse reaction will slow down a little bit. And as we build up some left side chemical, the forward will start to speed up, again reaching dynamic equilibrium, the moment at which the forward and the reverse reaction equal one another, and we can represent that also with the equilibrium expression. Notice that the quantities are different, but the quantities will indeed be proportional, giving us the same equilibrium constant. So here's a graph where 1 molarity of HI has been put in a container. We're representing HI on the left side and H2 and I2 on the right side. And as the reaction proceeds, HI will decrease and H2 and I2 comes in. This is actually two lines, one on top of the other. And how can you tell from this graph that this reaction reaches equilibrium? Well, the flat line or the parallel line or the fact that the quantities of the HI and the H2I2 have gone steady and are no longer changing tells us we've reached equilibrium. A second experiment in which we put some H2 and I2 in the container. 1 molarity again. Notice that those chemicals will decrease while the HI chemical starting at 0 is increasing. And what do you notice about the change in concentration of the reactants compared to the change in concentration of the products? Well, if the H2 and I2 are going down by about 0.8-ish, you notice that the HI has increased by approximately 1.6-ish. That 2-to-1 ratio, 2 times increase by the 1 time loss, is reflected, of course, in the balanced chemical equation. Next, let's look at a third setup in which we put 1 molarity of each chemical, so starting both chemicals at 1 molarity. And when this reaction starts off, how does the graph tell you whether the reaction moves forward or backwards? Well, a quick inspection shows you once again that the HI is increasing, meaning the reaction must be moving left, and the H2 and I2 are decreasing. Again, you can see that 2-to-1 ratio of change. And let's look at a third trial in which we're starting with random quantities. There's nothing special about the standard condition. We could start with any conditions. And so you can see that reaction here. Again, the 2-to-1 change. Here's the HI forming and the H2 and the I2. Now you can actually see both lines. They're not lined up on top of one another, but we've got I2 decreasing, having started at 0.8, and H2 starting at 0.3, also decreasing. What can you say about the equilibrium quantities in all three trials? Well, we can at least notice that there's always more HI and there's less of the right side chemicals. And while they're all different quantities, and we can notice that this guy, the HI, is larger than the H2 and the I2 each time, we're wondering, is there any other relationship? And where's this equilibrium constant come in? So here I've calculated, I've taken all the values from all these trials, put them in a chart, and then plugged them in one by one into the equilibrium expression, which of course is right side chemicals over left side chemicals raised to any coefficients. And doing the math with these chemicals, we get 0.0185, and it pops up again and again. In my opinion, these are all pretty darn constant. And so our equilibrium constant calculates from our equilibrium expression. Notice that the KEQ is smaller than 1. That stands to reason because the right side chemicals are all less. And so we'll ask you in this unit, is KEQ bigger or smaller than 1? Unlike in the last unit with G, S, H, and E, we were thinking about positive versus negative. You'll never get a negative value for K because you can't have less than 0 chemical. So K values are always positive, but the question is bigger or smaller than 1. And when a K value is smaller than 1, that tells us that this is a reaction that favors reactants, left side, and not so favoring of right side. What's not the equilibrium expression is notice that we must include this 2 from our reaction. And if we didn't include it, you'll notice that you do not get constant values. Also, this is a multiply in the equilibrium expression. If you have 2 chemicals, even though there's a plus sign in the balanced equation, this is a multiply in the equilibrium expression. If I added, notice once again, do not get constant value. So we've got to pay attention to our stoichiometry and turn that stoichiometry into exponents. And we have to remember that if we have more than one chemical in our equilibrium expression, this is not a plus sign, it would be a multiply. We're at equilibrium and at standard conditions, where everybody was 1. Of course, K would be equal to 1. This just does not happen very often. There's so many other equilibrium position possibilities. The odds of being at 1, 1, and 1 are quite slim. What else do we need to know? Plenty of information that we want to know. First is these letters will give us some information. K or KEQ is generic, but if we are asked for KP, that will be for gases, and the units would be generally in atmospheres. P standing for pressure. Kc represents if we're talking about the molarity, which could also be gases, but is very often solution molarity. Later in this unit, we'll study Sp, which stands for the K for solubility product, chemicals that we're wondering about whether or not they dissolve. And in another later unit, G, we'll study the equilibrium constant for acids, bases, and water. Square brackets versus parentheses. AP can be a little particular. If you're asked to write an equilibrium expression for Kc, you should, by virtue of being given molarity values, you must use square brackets because, of course, you're well aware that square brackets means molarity. If, however, you're writing a Kp expression, you should be using parentheses and not using square brackets. You could pause the video, give this a try, write the Kc expression for this reaction, and write the Kp expression for this reaction. Hopefully you're able to produce these. Again, paying attention to parentheses for a Kp. it would be fine to leave the P off and just put the chemical inside the parentheses, but you would not ever want to use square brackets if you're talking about Kp. We want to be with parentheses. What about units on the equilibrium expression? The short answer, and you can certainly fast forward the video, is none. We're not going to put units on the equilibrium constant because those units would turn up to be different in many different situations depending on what molarity values or ATM values, pressure values we're using, and they don't really have any meaning. Well, after all, what is a 1 over molarity cubed? We don't really know what that is, so we're going to leave the units off. And this is one of our few naked numbers. We've already seen that absorbance does not carry any units, and nor later we'll work with pH, and those do not carry units. And that's because these are logged values, and the log of a unit doesn't really make any sense. We've already said large equilibrium constants tell us that the equilibrium lies far to the right, and anytime we get an equilibrium constant 10 to the third or greater, we'll assume completion. Anytime we get a value of 10 to the minus 3 or smaller, we'll assume that reaction hardly gets started. We may even see equilibrium constants as small as 10 to the 30, 10 to the minus 30, 10 to the minus 40. When we have significant quantities of both, of course, we'll get intermediate values, 200, 10, 0.1, those kinds of values. So how constant is the equilibrium constant? Well, it's constant unless you vary the temperature. Of course, unique to each reaction, not to say two reactions couldn't have similar values, that's certainly true. But the equilibrium constant does not depend on the initial quantities because you've seen those will end up proportional, and the equilibrium constant doesn't depend on using a catalyst or not. Using a catalyst would simply get you faster, so the reaction will get faster to equilibrium when a catalyst is used, as represented by this dashy line. And of course, the equilibrium can be reached from going in the reverse direction. Either way, we can end up at the same equilibrium constant. So it only varies with temperature. So in a lot of these problems, you'll be given a temperature, and often you're not actually going to use that number anywhere in your calculations. And distinguishing the equilibrium constant, K, constant in German is spelled with a K, from the equilibrium position. There's only one equilibrium constant for any given reaction, the actual value of K, but there's an infinite number of equilibrium positions. Any set of values, well, not any, but many different sets of values can actually end up at the same equilibrium constant. We'll call the different values the equilibrium position, and we'll call the actual K value the equilibrium constant.